So I think we can start. Hi, everyone, and welcome to our today's session organized by 𝐭𝐸𝐵 community. My name is Daria, and I'm so glad to see you all here. Today, we're going to learn about the world of artificial intelligence and machine learning. We will start exploring the process of testing these technologies that we use more and more, not only in our daily lives, but in our work lives. Today's session is the first event out of two. During our today's session, we will cover the 𝗫𝐶QB-based theoretical material, and on 23rd of May, we will have a second session, a workshop, where our presenters will show us how all this works in practice. So join our 𝐭𝐸𝐵 community and stay tuned. Now, I would like to introduce you to our speakers, Silvia, a software test automation engineer, plus she is an 𝗫𝐶QB certified AI testing engineer, and Victor, a lead software test automation engineer. Before we get started, I want to highlight that if you have any questions about our today's topic, don't hesitate to post them in our chat. In that, we will have a Q&A session, and we'll try to answer all your questions. So let's get started. Silvia, passing the word to you.
Okay, thank you very much, and thank you for the introduction. Yes, I'm a test automation engineer at 𝗫𝐴M and also an 𝗫𝐶QB AI testing certified tester. And all I'm gonna tell you is based on the content of the 𝗫𝐶QB AI testing syllabus. It's something that you can download for free from the 𝗫𝐶QB official site. So if you are interested in the topic, I encourage you to do so and study the materials. There will be three parts of this presentation. The first part, I will talk about AI in general. The second part will be dedicated to AI testing. And the last part will be a practical demo held by my colleague, Victor. Okay, so let's get started. First, let's talk about what AI and AI effect means. Currently, the AI is a system that has the ability to learn, understand, and use the information it has. But the understanding can change as technology evolves, and that's why I'm saying current definition. So the AI effect is this change in understanding of what is AI. A good example for that is the Deep Blue chess machine. It was invented decades ago, and it became very popular and well-known because it could play chess really well, actually that well that it could beat the world champion back then. But the thing that it was conventionally programmed, so it wasn't learning from data. So based on our current understanding, it does not count as an AI anymore. So it's a very good example to the AI effect. And since then, AI has come a long way. I'm sure that when you were shopping online, you encountered some recommendation systems and also chatbots and virtual assistants. Also, AI is behind like Siri or Alexa, for example. And AI has even become smarter with the advancements in deep learning and neural networks. It's very special because neural networks basically mimic the way our brain works to process data and make decisions. So it was a pretty huge deal. And it's now used in many AI applications like understanding and responding to spoken or written language, and even in self-driving cars. And one of the most current advancements is generative AI. I'm sure that you've already used ChatGPT or DALL-E, for example. it's able to create things that look or sound like they were made by humans, to simply put this. Okay. And when it comes to the types of AI, we categorize them into 3 groups: narrow AI, general AI, and super AI. Narrow AI can perform a specific task very well, but only in a very limited context, like, for example, recognizing a face or suggesting a movie. And this is the type of AI that we see and use today. The second type is general AI, or AGI, which would already will have similar cognitive abilities like a human and can understand the world around it in a broader context. However, this type of AI mostly exists in science fiction at the moment, unfortunately or fortunately. And lastly, there is super AI, which is totally just a theory for now. It would not just perform any intellectual task a human can, but also outperform humans. So it would have great computing power, practically unlimited memory, and access to all human knowledge. But why AI is such a big deal? Because conventional computer systems and softwares are programmed by humans using a programming language, which includes well-known constructs like, for example, if-else or loops, which are very easy to humans, or at least for programmers, to understand how the system transforms inputs onto outputs. But in an AI-based system, patterns in data are used by the system to determine how it should react in the future to new data. And I also want to highlight that AI is not just about softwares, because also with the rise of AI, new hardwares were created that's suitable for AI, like application-specific integrated circuits and system on a chip. These are specific solutions, have features such as multiple cores, special data management, and the ability to perform in-memory processing. And also special policies and regulation had to be created to make sure that we can utilize AI safely. So yeah, I wanted to highlight that it's not just all about software. Okay, let's move on to the next slide, and let's check how machine learning and deep learning relates to AI. Yeah, we've discussed what's the definition of AI, but it's like an umbrella term. So it's like, as you can see on the image, it's like a huge circle of technologies. And then there's a smaller circle, machine learning. Machine learning is all about letting computers learn from data so they can make choices or predictions. So let's say you have a computer program watching lots of games of chess, and after seeing millions of moves, the program starts picking up the patterns and learn how to play the game itself without being explicitly programmed to do so. So that's ML. Within ML, there is an even smaller circle called DL, or deep learning. Deep learning is a little more complex. It involves something called neural networks. These networks are, imagine it like a factory assembly line. You feed information in at one end, it goes through several steps and pops out at the other end with the answer. So just like an assembly line makes small changes to a product as it moves along, each step in a neural network adds like a bit of learning, a bit of knowledge, until it comes up with a final answer. And the deep in DL comes from having lots of these steps where learning takes place. Okay, and let's talk a bit more about machine learning on the next slide, which is about the types of machine learning. Yeah, so we talked about what is machine learning. And there are three types: supervised, unsupervised, and reinforcement learning. Let's start with supervised learning. So picture supervised learning like teacher-student scenario. The teacher show images and telling what is in the image, and the student, which is now the ML model, learns from label data during training. So it's like you show the ML model a picture of a dog, and you also show the label that it's a dog. So the system will find out and will understand what a dog looks like. And when the model is shown a similar picture, in the future, it could tell if it's a dog or a cat. So yeah, it sounds simple. But the problems solved by supervised learning fall into two categories, which is classification and regression. Classification involves putting data into predefined classes. Like, for example, this dog example that I mentioned is a good example to this. But like also a good example is to figuring out if a picture is a face or not, and telling the difference between an apple or an orange. There is another type, though, regression, that requires a model to predict a numeric output. So it's like guessing a person's age based on their photo. This was supervised learning. Now let's move on to unsupervised learning. So unlike supervised learning, this learns from unlabeled data. So jumping back to the previous example is like you are just showing the image of a dog, but you are not showing the label that it's a dog. But still, the system will be able to recognize the similarities and group the images based on these similarities. And here too, we have two problems that can be solved: clustering and association. Clustering is like separating groups of data based on something that they have in common. For example, like grouping dogs. The system doesn't know it's a dog, but they have similar ears, similar legs, similar tail, so it will know that they belong to the same group. Association is, for example, used in shopping recommendation system. When someone buys bread, let's say, they might also buy butter. So the system learns about this association and recommends items based on shopping behaviors. Okay, and there is a third type, reinforcement learning. It's kind of special because it does not use training data at all. Here, the system learns by interacting with the environment in an iterative way and learning from experience. And the system gets so-called reward when it does something right, and the penalty when it does something wrong. So over time, it learns how to improve. It's a common strategy used in robotics, autonomous vehicles, or chatbots. So to summarize, machine learning is learning from data. It can be supervised, but it learns from labeled data with right answers, unsupervised, where it tries to make sense of random data with no given answers, and reinforcement, where it learns by trying out things and learning from the results over and over. And remember, each type is suitable for different kind of problems and applications, like I mentioned. Okay. And now we are moving on to the second part, which will be all about AI testing and how it's different from testing conventional systems. So yeah, I've highlighted 4 specific aspects here, like test tools, test environments, test techniques, and challenges. But first, let me talk about AI testing in general. So firstly, it's important to know that AI applications are guided more by data than by logic. They need lots of different data to train and test their models, but sometimes it can introduce inaccuracies due to bias, noise in the data, or errors. Secondly, AI application keep learning and improving, which can change their behavior and outcomes over time. So it's extremely hard to get the requirements and the acceptance criteria right, because we don't really know that, for example, a self-learning system, how will change in the future. Lastly, they work based on probabilities. This means that the result they give can change depending on different inputs and context. So because of these reasons, testing AI applications are very complex, and they require new skills, approaches, test levels, techniques, and tools, and so on. So let's start with tools. Here, I would mention, for example, TensorFlow testing library that provides testing utilities for TensorFlow, which is an AI development framework. Also PyTest, which is a framework that makes it easy to write and run tests in Python. So these tools can help us to test the correctness, performance of AI application, and generate and manipulate test data too. The second aspect of AI testing is environments. Here, virtual environments are used because certain scenarios are needed when testing AI system. So let's think about self-driving cars. When we are testing self-driving cars, there can be dangerous scenarios. And we don't want to, so yeah, let's imagine that in reality you are testing a self-driving car. Obviously, you don't want to hit people, trees, and so on. So it's better to stay on the safe side and test it in a virtual environment. Also, there can be unusual scenarios. This can be tested when otherwise would be very time-consuming or expensive to set up in reality. Like, for example, you want to test how a self-driving car behaves if it's in a road intersection and, I don't know, 2 buses and 1 train arrives at the same time. It's kind of impossible to set up in reality, or at least it's very expensive. Or there can be extreme scenarios. This can be also impossible to set up. For example, you want to test how a self-driving car behaves during a natural disaster. It's also something to test, and it's also impossible to do it in reality. Also, there can be time-intensive scenarios, and with the help of virtual environments, this could be tested in reduced timescales, for example, several seconds instead of like days or so. And for these environments, we have both commercial and open source tools that are available, like Morse, AI Habitat, Drive Constellation, MATLAB, and Simulink. Okay, you can also see test techniques and challenges, but we are getting to it in the next slides. Okay, and now let's talk about AI characteristics and challenges of AI testing. So one characteristic is self-learning. Self-learning systems modify their performance over time, improving their ability to make predictions or decisions based on the exposure to new data. So they aren't directly programmed to perform these tasks. Instead, they use algorithms to learn from data inputs, experience, and then adjust their own parameters to improve accuracy. And it comes with lots of challenges during testing. First is unexpected change. The requirements are generally known, but there may be little or no information available on the changes made by the system itself. So it's really, really hard to design test cases properly. There can be also complex acceptance criteria. It may be necessary to define expectation for improvement by the system when it self-learns. For example, it may be assumed that if the system changes itself, its overall functional performance should improve. But after some point, these requirements can really easily get out of hand and becomes really, really complex. And another issue can be insufficient testing time. So if a system adapts quickly to a new environment, there might be insufficient time to manually execute new tests after each change. So usually these tests are automated. And let's talk about the second challenge, which is autonomy. The main point when we are talking about autonomy, it's that the system must be able to determine when they require human intervention and when they do not. And that's the most important to ask. And for example, when you think about, again, a self-driving car, it's a great example. So for a self-driving car, it should be there should be a timer set, like for example, after 15 minutes, it should ask for a human intervention because it's possible that the driver fell asleep, for example, and we do not want that. So it's necessary to do some time to ask for human intervention. For testing this, it can be well tested with, for example, boundary value analysis. Yes, and let's move on to the bias, which is another challenge. And bias, it's like an AI system having a favorite, basically. It happens when an AI system doesn't treat everything or everyone equally and prefers one thing over another. This usually happens when the data the AI learned from wasn't balanced. For example, if a facial recognition system was mostly trained on pictures of young people, it might not do so well recognizing older faces. So that's a bias towards young people. So AI needs to be checked for these unfair preferences because we do not want that. Sometimes even adding a good kind of bias to balance out any bad ones, or checking these biases involves looking closely at the AI training data and seeing where the training data comes from. And this helps us uncover any unfair bias within the data. Another very challenging aspect or characteristic is the probabilistic nature. It refers to the fact that many AI systems make decisions or predictions based on statistical probabilities derived from the data they've been trained on. For example, an AI system trained to identify images of dogs doesn't categorically state that this is a dog based on its training. Instead, it might say that there is a 90% chance that this is a dog, reflecting a degree of uncertainty. And actually, it has a good side too, because it enables AI systems to handle uncertainty, manage diverse and complex real-world data. So it's not always a problem, but in testing, the problem is that there may be multiple valid outcomes from a test with the same set of preconditions and outputs. So this makes the definition of expected results more challenging and can cause difficulties. And the last one is the transparency, interpretability, and explainability. AI-based systems are typically applied in areas where users need to trust those systems. And most users are presented with AI-based system like a black box. They don't really understand how they work. And it's a serious issue because to use like a self-driving car, of course, you have to trust this until some point. And it has led to the field of explainable AI or XAI. And the aim of XAI is for users to be able to understand how AI-based systems come up with the results, so increasing users' trust in them. And there are three separate terms. There is transparency, which is about determine, like how easy is it determine the algorithm and the data that was used. Also, there's interpretability. This is considered the understandability of the AI technology by various stakeholders, including the users. And there's explainability. This is considered to be the ease with which users can determine how the AI-based system comes up with a particular result. However, the understanding of AI-based system can differ depending on who needs to understand it. So testing for this understanding can be tough, and it's kind of a subjective matter because people have different abilities and may not all agree if an AI is understandable or explainable or not. And it's usually made by surveys and questionnaires, for example. Okay, now let's move on to the test levels. Here you can see that we have some conventional test levels, like component testing, integration testing, system testing, acceptance testing. But in AI testing, we have two extra testing levels. First is input data testing, but why it's so important to test input data? So let me talk a bit about ML workflow and data pipelines. It's a big topic, and maybe it will be a topic of the next session, but just some very quick introduction. So data pipeline is a system to automate the process of feeding data into machine learning models. So it's a sequence of data processing steps, and there are lots of steps like data extractions, which is extracting data from various sources. Also data cleaning and pre-processing that involves cleaning the data by handling missing values like inconsistent string formats or duplicate records and so on. And there is also data transformation, which is the third step here. It's when we transform the prepared data to our needs, basically, to put it simple. And there is also feature engineering. It's about creating new features from existing data. There's also model training, feeding the preprocessed data to ML algorithms to train. Also, at the end, there is model evaluation, model deployment, model monitoring, and updating. So yeah, my point is just that it's a very complex workflow, and there are a lot of steps. So to ensure that the data used by the system for training and prediction has a good quality, we have include some test types. Like for example, we have to do reviews or statistical techniques, like for example, testing data for bias. Also EDA of the training data. EDA is exploratory data analysis. It's an approach to analyze or investigate data sets to summarize their main characteristics, often using data visualization methods. Yeah, so it's very complex, but I hope that everyone has like a basic idea about this now. The second is ML model testing, and its goal to ensure that the selected model meets the performance criteria that has been specified. This includes ML functional performance criteria or metrics. Maybe for testers it can sound weird because like it's functional metrics, but we are also talking about performance here, which is like a non-functional test. But yeah, in AI we have such a thing like ML functional performance criteria. For example, it's the accuracy of the ML model or the precision of the ML model are good examples. And also there are non-functional acceptance criteria like speed of training, speed of prediction, computing resources used, and so on. And let's move on to component testing. But here I think maybe not so much to say because it's a conventional test level, which is applicable to any non-model components. Also, there's integration system, which is also a conventional test level, which is conducted to ensure that the system components interact correctly. It's important to mention that, yeah, we have AI systems, but often these systems have both AI and non-AI components, and we have to check if they are able to interact correctly. Also, another conventional test level is system testing, is to check that our system performs as expected in a test environment. And also acceptance testing, that's also a conventional test level, and it used to determine if the complete system is acceptable to the customer. But as I said, for AI-based systems, the definition of acceptance criteria can be really, really challenging. Okay, and now let's talk about some specific test techniques that are used in testing AI. First, let me start with adversarial testing and data poisoning. They are kind of similar. Adversarial testing is when we have a valid input for the already trained ML model, but we also add some carefully crafted noise to it. We call it perturbation, by the way, and it's designed to cause the system to fail. So, for example, here you can see we have like a valid input, a lion. We add some perturbation in the forms of, I'm not sure if it's very visible, but there are some pixels. And these extra pixels will cause the AI to fail and misclassify the lion to an elephant, for example. So in other words, it's about finding and exploiting the weak spots of AI models. It has two types, white box and black box. In white box, we know the algorithm that was used to train the ML model, and we use this knowledge to generate the perturbation. But there is also black box when we don't know the algorithm, but we explore the model to determine its functionality, and Then we build a duplicate model that provides similar functionality, and then use the white box technique. It might sound strange, but these perturbations are often transferable between models, so it might work. Also, there's data poisoning. It's similar to adversarial testing, and in some documentation I've also read that it's basically a type of adversarial testing, but there's an important difference that while for adversarial testing, we already have a trained model. In data poisoning, we are manipulating the training data, so the ML model learns incorrect patterns too. So it trains the model in a way that it will perform actions that the attacker desires. For example, misclassify certain classes. And there is also a good example for that. Maybe you remember that a couple of years ago there was the Microsoft 𝗕𝗂𝗏𝗏𝗏 incident in 2016, and it was basically an attack, but it was with malicious intent, but basically the technique is the same. And harmful Twitter conversation trained the system through feedback, and then it provided like wrong and inappropriate conversations in the future. And after this, it was shut down, this chatbot. Okay. And let's move to the next slide, which is back-to-back and A and B testing. They are quite similar techniques. Both back-to-back testing and A and B testing are used to compare different versions of the system, but they have key differences. Back-to-back testing, it's about comparing the results of two versions of the same system under the same conditions to ensure that the newer version is functioning as it should. So, for example, maybe you have an old conventional system that is not AI-based, but you want a new system that has the very same functionality, but you want to add AI to it. And so importantly, back-to-back testing doesn't necessarily aim to find out which version is better, but rather a new version is consistent with the old one. So it's to ensure that the new system hasn't unintentionally changed anything. So basically, it's kind of like regression testing. Also, there is A and B testing. In A and B testing, there is no old or new. This can be systems that were built like parallelly, and it's like an experiment that compares two versions of the system to find out which one performs better. Each version is exposed to different group of users in order to judge which version provides a better user experience or better metrics. And the goal here is to make an improvement and not to validate consistency. So in summary, back-to-back testing focuses on making sure changes or updates haven't broken anything, while A and B testing is about seeking improvements. Okay, now let's move to another really interesting test technique, which is metamorphic testing. When we are performing dynamic tests, we have an actual result that we compare to the expected result. But what if we don't have the expected result? That's what we call a test oracle problem. Test oracle is a source to determine expected results of the software under test. An oracle might be an existing system, other software, documentation, or individual specialized knowledge. And when it comes to testing AI systems, we often don't have that, but we have a large number of test cases. And we can also assume that for similar test cases with similar data, we also have similar output. So we can kind of assume the expected result. So rather than comparing the actual and the expected output, metamorphic testing exploits properties and relations of the software that should be true across multiple executions. These properties are known as metamorphic relations. Okay, and at the end, I also want to mention two test techniques, but these are actually known in conventional testing as well, so I'm not going to talk very long about this. One is experience-based testing, which is based on testers' experience, knowledge, and intuition, and it includes error guessing, exploratory testing, and checklist-based testing. I would mention here EDA. I think it was on one of the previous slides. That is the exploratory data analysis, which is an approach to analyze data sets to summarize their main characteristic, often with visual methods. So it's something that's used here. Also, there's pairwise testing, which is a black box technique in which test cases are designed to execute all possible combinations of each pair of input parameters. And it's something that often used in self-driving cars or vehicles. Okay. And actually, that was the end of the theoretical part. So now Victor will present you the practical demo. So Victor, the stage is yours.
Thank you. Thank you, Sylvia. Hello, everyone. Yep. So give me my screen, please. Thank you. Yeah. My name is Victor, and I'm a lead test automation engineer in 𝗏𝗏. I worked with API testing, web UI testing, mobile testing, and for the last 2.5 years, I'm interested in machine learning, and I worked on various projects involving machine learning models, neural networks, and big data pipelines. So today I would like with you to discuss a little bit about machine learning project and how to train and test neural networks. Also, we would like to see some machine learning tools which can be useful on the machine learning problems. But I would like to have a little disclaimer that this is part one. And in this part one, we would not go into much details. It's for intentional purpose because we would like to have some general overview on machine learning projects. And if you are interested how to test some specific machine learning architectures like computer vision problems, language processing problems, and very popular now large language models. Please join us on part 2 when we would discuss how to test each of these models in specific and what test types, what libraries and evaluation technique you can use for each of these problems. Yeah, so let's start from machine learning toolset and libraries. If you start with on machine learning project, in 90% you should know Python language because mostly it's done in Python language. And if you are interested in automation role on that project, it's all those tools which we would talk today would involve Python knowledge. And the first one is tools for experiments. And what is experiments? Sylvia told us that there are different types of machine learning problems, like classification, regression, and each of these types is split into some different subtypes. Like classification can be on computer vision. You can predict some images. You can predict some just numbers or prices. You can predict age of person. You can predict some types of diseases and so on. For each of that problem, to know the best machine learning algorithm, you need to have a lot of experiments. You should try a lot of different types of machine learning models. You should try different architectures, and basically data scientists and machine learning engineers, they are doing a lot of experiments. And we as test automation engineers and QA engineers, we should help them to define quality of each model. And for these experiments, it's very useful to use such tools called 𝗏𝗏𝗄𝐻. And this tool, it's basically this tool here. And what is 𝗏𝗏𝗄𝐻? And it was called previously like Jupyter Notebook. This is a server running on your local machine, and it has a web UI, this client, and you can use this tool for writing Python code. And you ask what is specific about tool for writing Python code, but magic of Jupyter Lab is that you can write this Python code and immediately execute it. So here you can see that we use Pandas library. Pandas is very popular library for data manipulation, working with data set, and retrieving data from different formats and converting to any other formats. So here we use Pandas to read data from JSON, and when we read this JSON, we just would like to have a look into first 5 rows of that data set. And you see that we call this function, and we don't need any print function. We don't need to go to console to look into a result of execution of that function. We just have a function here, and this magic of this tool, Python notebook, Python Jupyter Lab, we have here result immediately. And this Pandas allows us to do some filtering of data, some data manipulation. So here you can see that we've done some filtering. We check is it false or not. Also, there's another popular library, 𝗶𝗏, for image reading and converting it to binary format for using it image encode. And so it's very simple library. You just get a path of your image to that function, and you have this image in your memory, in memory of your computer. Yeah, and you can see that magic of by this Jupyter Lab notebook. It allows you to see this image in the notebook without any other tool. So, and I would like to mention another very similar tool called Colab. It's from Google. And what it is, it's the same Jupyter Lab notebook, but it's stored on Google servers. And why do you need to run anything on Google servers? Because specific of machine learning problem, to run this problem and to train your neural network, it requires video card, GPUs. And basically, if you don't have GPU on your local machine, or you don't have, or you have some old video card, you are in trouble because you will spend a lot of time to train this neural network. And here, Google can help you. And because Google provides you a free GPU, basically it's T4 video card. You can use it for your experiments. Of course, it's not very good when you run your machine learning problem in production, because it's free and it's not guaranteed to be available every time. So, but when we talk about experiments, it's very good tool to try different machine learning problems here and on some free video card. Yeah. Moving on. We've seen that pandas, there is some other libraries like NumPy, basically numeric Python, and PySpark. Numeric Python is a library for math operation on data, and it allows you to do linear algebra, basically. And linear algebra is basic of any machine learning problem. And PySpark is the most popular tool for big data manipulation. But today we would not talk about PySpark. It's better to talk in sphere of data quality. They have better experience with PySpark. And there are another tool for images like OpenCV. What is OpenCV? It's library. It's basically Photoshop for your images. If you have ever used Adobe Photoshop, OpenCV can do the same, but in your code. And Sylvia already mentioned TensorFlow, and there is another tool, PyTorch. It's the most popular net framework for creating neural networks. And today we will see how PyTorch works and how to use PyTorch for creating neural networks. So let me quickly show you what neural network is and how does it work. So let's say that we have such problem. This problem requires us to split orange and blue dots into separate groups. Let's say that blue dots are dogs and orange are cats, and how we would split them. So Sylvia told us that each machine learning problem starts from inputs. And inputs, what is inputs? Is basically if statements. So if this animal has specific tail, if this animal has is a good hunter, is this animal big or small, is this animal has a good smell, and so on, so on. So for you to have a context when you have a image and you would like to classify is it a dog or a cat on that image, you have a lot of these inputs. Basically, each pixel on that image is input. And if you have, let's say, 1024 image, like 1024 by height and 1024 by width, so you have 1024 to the power of 2 inputs. There's a lot of inputs, and bigger inputs, better we have result and better problem we can solve. So here we have only 2 inputs. Let's say that the first input divides this vertical line. It answers the question, is it a good predator or not? Is it this animal, is it good hunter or not? And second is it big or not? And we say that all cats are good hunters, and some dogs are good hunters. And some dogs are big, some dogs are small, but mostly cats are of the same size. So if it's big, animal and it's a good hunter, so very likely it's a dog. If it's small and it's maybe dog, maybe cat, and if it's bad hunter, so maybe it's very probably it's a dog. If you follow my logic, so you can have a lot of these ifs, and basically a real neural network has thousands of those ifs, and we have two outputs. Outputs basically trying to answer our questions. The first output trying to answer, is it a dog? And Sylvia already taught us that it's a probabilistic answer. It gives like 90% is a dog, 10% is a cat. So let's try to run this. And you see that our neural network trying to split our data sets. And it does pretty good job, but there are some mistakes. You see that this orange area, it has some blue dots on it. And some orange dots, they appear on blue side. So basically, we have some errors in our neural network. And to help our neural network to do a better job, we can add more inputs. Also, we can add hidden layers. What is hidden layers? Basically, it's a filters which group information. Like you see that the first input is connected with this neuron of hidden layer and this. So basically, we have a lot of ifs, and we group these ifs into hidden layer, and our neural network in these hidden layers trying to group information and to learn something about our problem. Like it trying to learn that all good hunters, and if it's big, it's probably a dog. So it groups information, and in the machine learning world, they said it generalized information about our problem. And when we run it, you see that it does a better job, because it splits our dots a little bit better than it was before. So it means that more neurons we have, it's easier for a neural network to solve our problem. But more hidden layers, more neurons we have, it's more computation demanding to train such neural network, because today's neural networks, they have thousands of hidden layers and billions of neurons, and it takes a lot of money to train such neural network. Okay, moving on. So it's was visualization about neural network, but how it works from code. And here we have another Jupyter notebook, and we have experiment to create a neural network which classifies dogs versus swans. I tried to be a little bit original, not dogs versus cats, because it's a very known problem. And here we have swans and dogs. So we have such data sets. You can see that we have some swans here, yes, and we have also dogs. Yeah. So, and we used PyTorch, basically a torch library, to train our neural network. So at first we create data sets. Here, there are different functions from PyTorch for creating data sets. Today we are not talking about them, but you should know that we have our train data, so to train our neural network, and test data and validation data. Test data, if we test our neural network after each train. So we train, we test, we train, we test, and we repeat this cycle like hundreds of times. And after we've done all train tests, we do validation. So validation comes in the end of our loop. Sometimes, yes, sorry, we do train and validation, train and validation. I missed order. And in the end, we do test like this. Yeah. Okay. We created our data sets, and we see that our data sets include some images of dogs and swans. And here we have our neural network. It's basically the same what we have here, but with different functional, like each of these neural network layer, it has a special meaning, and it's known to machine learning specialists, but today we would not talk about it. Here you have, we provide numbers of neurons and filters for each layer, and we do some magic of neural network, and then we define our function to measure accuracy of our model, how good it defines swans and dogs. Yeah, and so here we define our function for training, and here we do actual training. And as I already told you, there is a for loop: train and then validate, train and then validate. You see that here we have train and the evaluation, basically validation. And we just do it for 5 times because it's enough for our problem. Our problem is not very complicated for our neural network. And you see that our training accuracy is just 97%, so pretty good. And test accuracy is 100%. So it basically, this is how we test our neural network. It's very primitive, very general example how to test a neural network, but each problem requires different testing. So this testing only good for classification problem when we're trying to answer the question how good our model recognize dogs and how good our model distinguish dogs from swans. And you see that we have like all the best accuracy ever, 100%. In production, it's very unlikely you would have 100%, and even it's tell us about any other problem like overfitting. And about overfitting, we would talk in part 2. And overfitting is like it's indication that if your neural network is very good, you probably would have problem. And what problem we would tell you in next part. Yeah, and so we trained our neural network and we tested it, but we would like to have more specific test, not just a number 100, but we would like to test with different pictures. So here we have picture of this dog, and you see that it predicted a dog, and it predicted basically what it predicted. It predicted 2 numbers: the first number for dog and second for swan. And you see that for dog is a big number, and for a swan is a very small number. So, and we pick up the beta number. So if the first number is bigger than second, then it's a dog. If second number is bigger than the first, like here, you see, this is a swan. And here we trying to cheat on our model. So here we have a dog, but in a water. And when we pass this image to our neural network, it thinks it's a swan. And for dog, it's very small number. And let's try another image. Here, another image, and we pass to our neural network. And again, it's a swan. And for dog, it's small number. So why is that? And here we come to another technique, what Sylvia already mentioned it, about explainability of AI. We need to see into machine learning model and answer the question why it makes mistakes. And So here we use those four images, and we trying to visualize where attention of our neural network is is put on what pixels. And you see that red means that this pixel convince a neural network this is a dog, and blue it negative pixel. It convince our neural network this is not a dog. And you see that here eyes and nose and basically the body of our dog, it convinced our neural network this is a dog. And for Sven, we have very little, like almost invisible dots. And here for this picture, you see that this is not a dog because a lot of negative pixels. Basically, head of this Sven and wings and water. It convinced the neural network this is not a dog, but it's a Sven. But with these misclassified images, you see that basically a neural network paid attention to eyes and noses, and it thought that these eyes and noses belongs to dog. But there are a lot of white, and there are a lot of water. And our neural network thinks that if there are a lot of water and white color, it's basically better to say it's Sven, not a dog. So basically, we have a bias in our data set that our neural network thinks that if we have water and if we have a lot of white color, it's better to say this is a Sven, not a dog. So this technique and some other techniques for measuring neural network accuracy, we would see in more details in part 2. And for now, my practical part is over. And we can proceed to our Q&A session.
Thank you very much, Victor and Sylvia, for such an interesting session. Now let's switch to Q&A part of our event. But before that, I would like to pay your attention to the QR code you can see on the slide. We would really appreciate your feedback and suggestions. So please scan the QR and complete the survey whenever it's convenient for you. So yeah, let's switch to Q&A part. We have a question. Can I use C# for work with machine learning, or Python is a standard? Victor, we don't hear you.
Oh, yeah. Sorry. Yeah, I would try to answer it like, I would go with Python because most libraries like PyTorch, like TensorFlow, is written for Python, although in reality it's written in C++, and it can be ported to any other languages like which have some bridge with C. But it's easier to go with Python because a lot of tutorials, a lot of libraries, a lot of experience in already solved problems, they done in Python language. There are some tools for C#, for Java, even for JavaScript languages, which can do machine learning. But if you go with those languages, you would find it's very hard to find an answer for your question if you're stuck with problem, because there are no very experienced data scientists and machine learning engineers which have done some projects in other languages. So in production, I have never seen that some project would use anything else as Python or sometimes C++. But for C#, I have never worked on that project. But I have heard that there are some libraries for this purpose. Yeah.
Thank
That's
you,
all.
Victor, for the answer. Yeah, we have one more question. Is there any strategy to how select proper number of hidden layers and elements per layer?
I can go with it as well. I could. So it's mostly a question to data scientists, I believe, but I can try to answer that. You can decide with a lot of experiments. Like there are some specific algorithms to find the best architecture for your problem. Like it and how those algorithms they work. They trying a lot of different combinations. Like what should go with 100 layers? What if 1,000 layers? What if billions of neurons? But the problem is that if you can solve it with a few layers, go with less layers, because you would complete your experiment in less time, and you will train your neural network with less resources. If you have only 10 layers, or sorry, 10 neurons, and you can achieve like 99% of accuracy, go with 10 layers, because you would train your neural network in a minute. But if it gives you bad accuracy, like below 80%, try to add more layers and more layers till you till your accuracy is good enough for your problem. But still, there are some specific tools and algorithms which trying to solve this problem. But basically, there are libraries, and you would use library, and you say that try this from 10 layers to 1,000 layers, and this library would tell you that 55, for example, 55 layers is enough for your problem. Yeah, that's all.
Thank you, Victor, again. For yet, I don't see any questions. Maybe somebody is typing. Whilst that, I want to remind that please don't forget to leave your feedback by just scanning the QR code and completing the survey. We are really looking forward to hearing from you guys. And yeah, I don't see any questions. So if you happen to come up with any question a bit later, you can also leave your comments in via community event itself, or post them like your questions in the chat during our second session on 23rd of May. I can see thank you messages in the chat. So yeah, thank you very much, everybody, for attending this meeting. Thank you again, Sylvia and Victor, for this amazing presentation. I would like to remind you one more time that on 23rd of May, we will have a second session, a workshop, where our presenters will reveal more details on how AI testing works in practice. So don't forget to join our 𝗬𝗓 community to stay in the loop. Thank you again, everybody. Have a good day. Bye-bye.
Thank you. Bye.
Thank you. Have a nice day. Bye.